The next major discovery we made that helped further our understanding of electron organization is what we call the Heisenberg uncertainty principle, named after the German physicist Werner Heisenberg that first codified it. The Heisenberg uncertainty principle describes the relationship between an electron's position, where it is in time and space, and an electron's momentum, which simply put is how fast is the electron moving. And he codified this in this inequality that we see here, where delta x represents the change in an electron's position in time and space, and delta p represents the electron's change in momentum or change in velocity. And we can see, based on simple mathematical relationships, that change in velocity and change in position are inversely related to each other, because if we were to increase the speed at which electrons move, in order for this inequality to be true, the position would need to decrease. Well, how exactly does a position decrease? A better way to look at it is in terms of predictability. If an object is moving faster, for example, if we speed up the rate at which an electron moves, does it become easier or harder to predict where that electron is going to be? Well, the faster an object moves, and given that electrons move at the speed of light, you would expect that it would be harder to anticipate where electrons will be. And that, in a sense, is what the relationship states. So what this means is, as the velocity of an electron increases, as electrons move faster, it becomes harder to predict where exactly that electron is going to be. And we know that electrons travel at the speed of light, so the conclusion that Werner Heisenberg reached, which is why we call it the uncertainty principle, is that it is actually impossible for us to know the exact location of any electron. Instead, through much more complicated mathematics, Heisenberg determined that we can calculate the approximate probability, which is the likelihood of where the electron is. And from there, we end up with our second quantum number and a term that goes along with that. That term is what we call a subshell. So a subshell, which we represent here, is the 3D space in which an electron is probably located. Again, because this represents the likelihood that the electron is probably somewhere in here. So this subshell here, which is what we call an S subshell, represents a 3D space, and each one of these dots isn't exactly a single electron. Each of these dots is a possible location where an electron can be within this 3D space. Let's get to talking about what the actual quantum number is. So the second quantum number is what we call the angular momentum quantum number, which we represent by the variable L. So depending on what this number is, that changes what the actual 3D space in which we can find an electron is. So if we take a look at these 3D spaces here, we kind of see that these are 3D circles, also called a sphere. So if L is equal to 0, this is what we call an S subshell. Again, you can remember this because the letter S is the first letter in sphere. And if this is the 3D space in which the electron is probably moving about, we can fit within this 3D space two different electrons. However, not all subshells are this particular shape. Each of these subshells, yes, these three are actually one subshell together. We will talk about why they are separated, but each of these is what we call a P subshell. So if L is equal to 1, this is a different shape. These are decidedly not spherical, and each of these groups of 3, which make up one P subshell, can hold 6 electrons. Each of these, again, there are 5 different 3D spaces here, but all of these combined together are a single subshell, which we call a D subshell. And again, if our angular momentum quantum number is 2, this is what we call a D subshell, which can hold 10 electrons. The final subshell is what we call an F subshell, where if L equals 3, the F subshell can hold 14 electrons. Now, all of this is probably sounding like gobbledygook to you, but there is something that we can look at in the periodic table that can help you remember all of this information here. So here, we can see the periodic table broken into 4 distinct sections here. And again, if we remember the name of the first type of subshell, the first 3D space that can hold 2 electrons is what we call an S subshell. And if you count the number of elements across 1, 2, it is no accident that there are 2 elements per period in this when an S subshell can hold 2 electrons. And for that reason, we call this region of the periodic table the S block. If we go over to here, where we first see boron, carbon, nitrogen, oxygen, fluorine, and neon, we remember the name of our second subshell, the second 3D space where an electron is probably located, and a P subshell can hold 6 electrons. And if we count the number of elements across, 1, 2, 3, 4, 5, 6, again, this is not accidental, which is why this area of the periodic table is what we call the P block. Likewise, if we remember the name of our third type of subshell, the D subshell, which can hold 10 electrons, when we get to the center of the periodic table where our transition metals are, if we count the number of elements across 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, exactly matches the number of electrons that a D subshell can hold, which is why we call this the D block. And as expected, this is the section of the periodic table that is normally written below, because a periodic table that looks like this won't fit on most pieces of paper. But again, we see the final subshell, the F subshell. This 3D space can hold 14 electrons, and if we count the number of elements across, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, this is not accidental, which is why we call this the F block. In the next video, we are actually going to look at how we can use this information, both the principal quantum number, the energy level, and the angular momentum quantum number that describes where electrons might be in 3D space, and how we can actually use these numbers in order to start classifying electrons based on their distance from the nucleus and their probable location.